looking at an exact, continuous time function x of t, let's look at an approximation x hat of t that is equal to the summation of x of k delta times delta sub capital delta of t minus k capital delta times capital delta. Okay. Now, what is this thing here? Okay. So x of k delta is the value of x at the integer multiple of capital delta. Okay. So this is the value of x, value of this x of t at integer multiples of capital delta. Okay. Now, delta sub capital delta of t minus k delta, right? If you recall, delta sub capital delta is the very short pulse that we used to approximate a delta function before. Okay. So delta sub capital delta of t is this rectangular, short pulse, assuming delta is very small, with magnitude 1 over delta when t is between 0 and capital delta and 0 everywhere else. Okay? So delta sub capital delta of t minus k delta is this square pulse shifted to time k delta and then multiplied by delta, right? So when this capital delta is multiplied with 1 over capital delta, then we basically have a rectangular pulse with magnitude 1. Okay. So this thing here is essentially a rectangular pulse with magnitude 1, okay, at time k delta. Okay. And this rectangular pulse, if you scale it by the corresponding value of x at this time, then summing these rectangular pulses up will essentially give you this staircase approximation of the original function x. So again, x hat of t is this staircase function here that serves as a approximation of this continuous time function x of t. Okay. So do we have any questions about this? All right. So if your continuous time signal x of t is sufficiently smooth, then we can expect that as this delta, right, as this delta becomes smaller and smaller and smaller towards 0, then eventually x hat of t will converge to x of t as delta goes to 0. And this delta sub capital delta of t, right, which is the very short pulse that we introduced before, converges to the delta function as delta goes to 0. Now, suppose that we look at a particular value of t that is between m delta and m plus 1, that is between m capital delta and m plus 1 capital delta. Okay. So if you pick a value of t, suppose you pick a value of t here, between k delta and k plus 1 delta, then what is the value of x hat at this point? 那我刚才就想说，就是我刚才那个问题，就是说，如果我挑一个时间点 t 是介于 k delta 跟 k 加1 delta 之间的话，那 x hat of t 的值会是什么呢？就是我如果挑一个时间 t，就是我图里面画的这个，就是我如果挑一个时间 t 是介于 k delta 和 k 加1 delta 之间， right？ 那它的这个值，它的这个值会是什么？
是 x of k delta，因为它很
对，谢谢。
趋近于0。
对，没有不需要趋近于零，没有关系，就是说我只要挑 t 是在这个 interval 内的话，我只要挑 t 是在这个 interval 内的话，那 x hat of t 就是 x of k delta 这个值嘛。对，所以如果挑 t 如果说这个 t 在这个 k delta 跟 k 加1 delta 之间的话，那么 x hat of t 就会等于 x of k delta, right? All right, so this is what we're saying here. So if you here I'm just using m instead of k, right? So if you pick t between m delta and n plus 1 delta, then x hat of t should just be x of m delta. Okay, so hopefully no problem here. Okay, all right. Now, suppose that this x of tau, right? I'm using the time unit time index tau here, right? This x of tau, okay, is multiplied with this delta sub delta of t minus tau. Okay, so this delta sub delta is a rectangular pulse, right? This is a rectangular pulse with a magnitude 1 over delta. Okay, and because it's time reversed, right, and shifted to time t, it would look something like this, right? You would have a rectangle that is magnitude 1 over delta from t minus delta to t, about this m capital delta here. Okay, right. So if you multiply x of tau with this delta of t minus tau, okay, then the function you get is this function here. Is this function here. Now, if you take the integral, right, of if you take the integral of this function, right, you hope to obtain the area under this red curve here, right? And the area here can be approximated, right, assuming that delta is small enough, can be approximated by the rectangle at the same place with the magnitude that is equal to x of m delta times 1 over delta, right, which is the magnitude of this delta function here. Okay, so this area the area, which is this integral of x of tau delta of delta t minus tau d tau, okay, is approximated by the area of the rectangle, which is x of m delta 1 over delta times the duration, which is delta. And this is just x of m delta. Okay. All right. So what does this tell us? This tells us that if you take the value of x hat at time t, you will get this value x of m delta, which is actually an approximation of the area of this function here. Okay. So by this observation, this x hat of t, which is summation x of k delta sub capital delta t minus k capital delta delta, k from minus infinity to infinity, we can approximate this by the summation of the integral x tau delta t minus tau d tau delta t minus k delta capital delta. Okay? And the reason is because we're approximating this value here, right, which is given on the bottom right corner, okay, with this integral, okay, with this integral, okay, for a t that falls within the interval of k delta to k plus delta, because the value of t is confined by this rectangular function here. So if you recall, this part here is 1 only when t is between k delta and k plus 1 delta, and 0 otherwise. Okay? So for a t within this range, I can approximate x of k delta with this integral here. Okay. Now this integral, right, this integral has nothing to do with k, so I can bring this outside of the summation. And then when summing over these rectangles, right, over different time intervals, k delta to k plus 1 delta, k plus 1 delta to k plus 2 delta, and so on and so forth, the summation of these rectangles sum up to be a constant 1 function. Okay, so eventually this gives you just this integral x delta, x of tau delta of t minus tau d tau. Okay. So then consequently, as this delta becomes smaller and smaller and smaller and eventually to 0, we know from the previous slide that x hat converges to x of t. Right? We know that this left-hand side converges to x of t, and that the right-hand side, because this very short pulse converges to a delta function, the right-hand side converges to the summation, to the integral of x of tau times the delta function delta of t minus tau d tau. Therefore, we get this equation here, which is basically the equivalent of the shifting property in the continuous time case. Okay, so in this part, right, we're trying to extend the concept of discrete time signals, right, to the case of continuous time signals. Okay, so analogous to discrete time signals, right, where we can view discrete time signals as a superposition of these unit impulses, we can approximately view a continuous time signal as a superposition of these very short rectangular pulses, okay, with delta going to 0 in the limit. Okay. Now, this shifting property, right, you can actually obtain in a much simpler fashion, right? So the reason we went through the development before is because we wanted to draw some relation with the discrete time case. But actually, we were capable of obtaining this from the basic properties of the unit impulse that we introduced in chapter 1, right? Quite directly, right? Because if you recall using the techniques in chapter 1, right? If you take the integral of x of tau d of t minus tau d tau, right? We know that when you multiply x of tau with a delta function at time t, right, you will only get a non-zero value at time t. Okay. So this integral should be equal to the integral of the value of x at time t times delta of t minus tau d tau. Okay. And because t has nothing to do with tau, I can bring x of t outside. So this gives me x of t integral delta of t minus tau d tau. And because the integral of a unit impulse function, right, the area of a delta function is 1, therefore this integral is 1, and therefore this is just x of t. Okay, so this is a simple way to derive the shifting property, right? X of t, okay, x of t equal to this integral here. Okay, using the basic properties of the unit impulse that we discussed before. Okay. Right. So you know, even though we could have attained this shifting property much easier in this way, but going through this development, it allows us to draw some relation with the discrete time case. So, like I mentioned, you know, by viewing it this way, right, we can view a continuous time signal as a superposition of these very short rectangular pulses, right? As a superposition of these very short pulses. Okay. So if the input signal is a superposition of these very short pulses, then the output signal should also be the superposition of the corresponding responses of these very short pulses. Okay. So again, if you view the input as a superposition of these very short pulses, then the output should be the same superposition of the corresponding responses of these very short pulses. So suppose that we denote this h hat sub k delta of t as the response to this very short pulse at time k delta. Okay. So suppose that h hat sub k delta of t is the response of the linear time invariant system to this very short pulse. Okay. So then by the superposition property, the response to this x hat, right, which is a superposition of these very short pulses, is then a superposition of their corresponding responses. Okay. All right. Now, assuming that, you know, for delta that is very, very small, approaching 0, right, we can approximate this very short pulse as a delta function at this time, and therefore we can approximate its response as the response to this impulse at time k delta, right? So if you recall, this h sub k delta of t is the impulse response to the response to the impulse at time k delta, right? Which is this impulse here. Okay. Then this y hat can be approximated as the summation of xk delta hk delta of t delta. Okay, so we're approximating this h hat with this impulse response h sub k delta of t, right? Then as delta goes to 0, this summation here, which you can essentially view as a Riemann sum, right, converges to the Riemann integral, right? So as delta goes to 0, this summation above, right, which is the summation of these, rectangular strips, right, is the summation of these rectangular strips here. Okay, converges to the integral of this continuous function here, which is x of tau, h sub tau of t, d tau. Okay. So this is the response, the input-output relation when we have a system that is linear. Okay. Now, if you have a system that is further time invariant, then this response to an impulse at time tau would then just be a time-shifted version of the response to an impulse at time 0. Okay. So this is saying that if your system is further, time invariant, okay, then the response to an impulse at time tau, which is h sub tau of t, would just be a time-shifted version of the response to an impulse at time 0. Okay, so this is all the same as before. Okay, so if you substitute h of t minus tau into h sub tau of t in the previous slide, then the input-output relation can then be written as this integral form here. Right? So the output y of t is equal to the integral of x of tau times h of t minus tau. Okay, and this is conveniently written as x of t, again with a star or asterisk, times and this h of t. Okay. So this is the equation that describes the input-output relation in a linear time-invariant system. Okay. And this integral here is referred to as the convolution of the signal x of t and the impulse response h of t.